Welcome to the presentation of our paper Runtime Assessment of the Parameter Utilization and Adaptive Systems. My name is Martin Goller and I will lead you through this presentation. Okay. What are we going to talk about today? First of all, I'll give you a short introduction with a problem statement, a solution idea, and a basic approach. Then I'll come to the core of the paper, the measure with the idea and the definition. And finally, I'll show you a short evaluation. The main context of our paper is self-adaptive and self-organizing multi-agent systems, and we focus mainly on the self-adaptation part. Behind everything is the main problem. We assume self-adaptation may change the observable behavior of a multi-agent system, and that unexplained changes in the behavior may lead to a decreased user acceptance. For example, a red traffic light, which takes longer than expected, then you might ask, why does it take longer? Maybe it's broken. So at this point, it would be nice to have an explanation. The solution towards such an explanation scenario is as follows. We assume that normal self-adaptation has no major impact on the behavior. So we need to identify unusual self-adaptation in the system if something occurs that needs an explanation. So if we have such an unusual self-adaptation identified, then we need to identify the root cause. And finally, we want to create and present an explanation to the user. The paper focuses at the identification of unusual self-adaptation. The approach to give such an to identify such unusual behavior is the idea that the agent's behavior is influenced by its configuration. Each agent is a technical system and has an internal configuration, and this configuration reflects the behavior. So to identify unusual self-adaptation, we want to measure configuration changes. And we need to use several measures to get better results in identifying abnormal configuration changes. So the idea for this measure we are presenting is that we take all configurations of all agents at a given time, and we assume that during normal operations, these configurations stay in an usual range of values. So if some configurations leave this range of usual values, then we assume that something is going on, which we need to look at. And we want to identify such change events at a global scale, not at the scale of a single agent, but at the scale of the whole system. So the main part of the paper is a measure to identify unusual changes. The definition starts with fixing a point t in time and a window size, L. And then we take the set of all configuration vectors for all agents. And we assume that these configuration vectors are n-dimensional and that all agents are of the same kind, identical. That means that all the entries in this n dimensions have the same meaning for each index. Then we will fix one of these entries in the n-dimensional vector, namely index j. And then we calculate the range of possible values for this configuration entry. These possible configuration values are fixed at design time, either by the choices of the system architect or by physical limitations, such as temperature may not drop below 0 degrees Kelvin, or other technical limitations, such as a Boolean value can only have two values, 0 and 1. After identifying the range of possible values, we then look at the current time frame we are looking at, and in this time frame we take all values that the agents take and calculate a range for these actually taken values, the maximum of all taken values and the minimum of all taken values, and this is our range in this current time frame. And this leads us directly to the quite simple definition, which we call the global parameter usage, which is the fraction of the actually used parameter range divided by the global possible parameter range. Then we have a second measure defined, which we call the average parameter usage. It's quite the same, but we look at each agent on its own and take the range that a single agent takes in the current time frame. And for all the ranges that the values take for each agent, we calculate the average and then divide it again by the possible value range. Picture says more. This is a short example of how to calculate these. Let's assume we have a possible range of 10 values, the red range on top, and our system consists of 4 agents. Each agent takes a smaller range of values in our current time frame, such as agent 3 uses only 4 of the 10 possible values. Agent 4, the last green range, is 2 of the 10 possible values. This gives us then a global parameter usage of 0.5, calculated as the yellow range, 5 actually taken values, maximum and minimum, divided by the 10 of possible values. And the second measure, the average parameter usage for these 4 agents, is the average of the green ranges divided by 4, and then divided by 10, which leads to an average parameter usage of 0.275. We note that we are not interested in the actual values of these global parameter usages, but in the time series and in changes in these time series. We assume that detectable notable changes in the time series leads to hints towards abnormal configuration changes. So we have an evaluation section with 2 scenarios. The first scenario is a smart camera scenario. We call it the night at the museum. And the second one is a traffic simulation. To both scenarios, we apply 2 free measures, the 2 parameter usage measures of this paper. And for comparison, one of our previous measures, which we call the configuration stability measure. Scenario 1, the cameras. We have 10 smart cameras watching 2 hallways. The picture shows it. The small black circles are the cameras, 5 on each left wall of the 2 hallways. The triangles are the view range, the viewport of the cameras. These cameras are able to track persons which are in range, and they are communicating with each other to minimize the overlap of the monitored area, such as 2 cameras should not monitor the same area, but maximize the globally monitored area. The scenario has a guard and 1 intruder, and the intruder is trying to sneak past the cameras. The cameras are monitored by a system which uses the stability measure to identify unusual behavior. And the intruder is an insider. The intruder knows that this is used and then hacks into the cameras to turn them away from his path. And he's smart enough to manipulate the cameras in such a way that that does not impact the calculation of the stability measure. And this attack in the simulation happens from t equals 110 to 120. So what does it look like in our measures? First of all, the stability adaptation, the adaptation stability measure. Two graphs here. The red one is the normal behavior, the expected behavior. Let's say this is the one that from the night before. Everything is as usual. And the blue graph is the outcome of the hacked simulation. We can see the intruder really is smart enough. During the time frame of the attack, 110 to 120, the impact of the hacking is not visible. It only becomes later visible after 145. On the other hand, we have the global parameter usage with a window size of 5. Again, a hacked and a normal graph here. The blue one shows a small impact of the hacking, but it's not very visible. But in the second measure, the average parameter usage, the attack is really good visible. Then we have a second evaluation of the traffic simulation. The traffic simulation consists of a street network with 30 intersections. Each intersection minimizes the waiting time for the cars at the incoming lanes. And the configuration which we are looking at are the red light times. There are, of course, cars in the simulation, which are part of the environment, not part of the system. There are 250 cars driving around randomly. They pick a destination and then drive the fastest way towards it. And when they arrive at their destination, they choose a new one. The simulation incorporates a rush hour scenario. So we define 2 time points. The first is T 250, where 500 new cars appear and drive from designated starting points called the homesteads towards their workplaces. And in the evening, a second rush hour, the same happens, but at the opposite direction. What does it look like? This is the graph of the street network. Let's say there are 2 islands connected by 3 bridges. On the left side, we have the 3 designated homesteads intersections. On the right side, the workplaces. And in the morning, the homesteads spawn 250 cars, 500 cars at t equals 250, which then start to drive from left to right. And in the evening, we have the same in the opposite direction. At these 2 time points, we have increased traffic flow, which causes each intersection involved in the increased traffic flow to reconfigure their red light times. Here again, a graph. First, the configuration stability. We can see that the rush hours show in the graph with 2 very high peaks, but there are other quite prominent peaks which come from the background noise of the other cars driving around. So this configuration stability is not very good at identifying this unusual event. On the other hand, the global parameter usage is way better to identify the 2 rush hours, while the background noise does not impact the graph very much. And finally, the average parameter usage is also not very good. It does identify the evening rush hour, but the morning rush hour at 250 is barely visible in the background noise. So the conclusion of this paper, the presented scenarios The new measures give better hints for disturbances than the stability measure. In the camera scenario, the average parameter usage shows better insights. In the traffic scenario, the global parameter usage is better. We have other scenarios which are not presented in the paper where the stability measure gives better results. So we can say that these two new measures are a good addition to our measurement framework, which we wanted to use to identify unusual adaptations which cause unusual behavior in multi-agent systems. So this is a video recording. I can't answer your question, but I hope you enjoyed it. Thank you for listening.